Okay, morning everyone. I hope you had a good weekend. So how's milestone 3 going? Hopefully everything's going well. You still have a little bit of time, so hopefully things go well by then. Okay, we're gonna continue talking about milestone 4. And last week, if you remember, we talked about, we introduced what the problem spec is, and we studied one of the approaches to tackle this problem, which is like the greedy algorithm. And today we're going to continue talking more about how to more accurately estimate the travel time between two different intersections, and then introduce more complicated heuristics that would give you a bit more quality. Okay, so if you recall at the end of the last lecture, basically we talked about can we do better to accurately estimate the travel time than the geometric distance between two intersections, right? So that's what we used in the greedy algorithm, and it showed us that we were able to finish all of the algorithm within 20 seconds. And it was quite fast. The problem is with the problem with geometric distance, it's a reasonable heuristic, but it's not as accurate. So you might lose a little bit of quality. And we benchmarked this. It's about 5% actually in terms of quality if you don't model the travel time between the different intersections and the problem accurately. Okay, so can we do better than this? And this was an example of why we would lose a bit quality. So let's say that two of the intersections are across a highway, and if you just rely on the geometric distance, then your estimate will be around 300 meters over 60 kilometers per hour. But in real time, to go from one intersection to the other, it takes longer because you want to get around the highway. So we are losing a bit more quality here in terms of our estimation, and our greedy algorithm may not perform as good. Okay, so we introduced one of the ideas, which is called memorization. Memorization is a very popular technique in computer science in general. And you used it a lot in milestone 1, I think. Whenever you want to make things faster, try to prefetch the data that you might use earlier on. Okay, and in this case, it's the same thing. Can we pre-compute all the shortest paths that you might need between any two different intersections in the problem, such that whenever we want them during our milestone 4 optimization, we can just query them quickly through a hash table or in an O of 1 axis. Okay, and we said that we're gonna build this kind of matrix where it will give us the travel time taken based on our milestone 3 optimization from any intersection in the problem to any other intersection. Remember, we have n deliveries, so we have around 2n intersections because of the pickup and drop-off locations, plus d depots. So all of these are intersections that we might want to visit from one to the other. Okay, so we build this huge matrix through milestone 3 to be able to make the travel estimation more accurate and faster access. Okay, now the problem is, how can we do this for every single intersection? And the number of those intersections can be big, right? So if we rely on the single source, single destination find path, which is whatever you are building in milestone 3 right now, what do we know here? So we need any delivery location to any other delivery location, the travel time for this. So we have around 2n intersections, where n is the number of deliveries, and so that's in the order of n squared. That's around 39,000 calls, right? We're gonna call the find path around that number. Plus, we need any depot to any delivery location, so that's an additional 2n times d calls, so that's around 2,000, plus any delivery to any depot, so that's around another 2n times d. And in total, we have 43,800 calls to M3 function in order to build that matrix. And that matrix will help us better accurately model the travel time, right? But if we say that our fastest implementation is going to be around 100 milliseconds, which is fair enough, then this is going to take 4,380 seconds. And that's obviously not a good solution because we are constrained with the 50-second constraint in milestone 4. So it's still too slow. So we introduced the idea of doing multi-destination from a single Dijkstra call. So if you remember how Dijkstra works, basically we do a wavefront expansion around the source intersection that we're starting at, right? So we start from here and then continue looking around all of the intersections around us, and Dijkstra is a bit smart because we will not visit the same intersection twice because we are ordering the priority queue in a smart way, right? Until we reach the destination here. But what do we know in this case? At this point, we know that we can find the shortest path to any intersection inside these wavefronts by just backtracing from that intersection back to the source, right? Because that's how Dijkstra works. Dijkstra guarantees the optimality of any sub-solution as long as you haven't reached your destination yet, right? You can build your final solution out of smaller optimal solutions. And in this case, Dijkstra is more useful to us than A-star because A-star is more directed towards the destination and we might end up not visiting most of the intersections, right? But while in Dijkstra, in this case, we want to visit all of the intersections because it will help us try to cover all of the intersections of interest in this milestone. Okay, so if we can continue, if we don't stop there, since we know that Dijkstra gives us the optimal solution to any, go ahead, you have a question?
Yeah, so let's say you're finding the shortest distance to every node in the one in the center.
Yes.
And you get to the node that is furthest away.
Yes.
And you're going to keep going beyond that. How do you know when to stop?
So in milestone 4, you know all of the intersection of interest that you want, right? So as long as you haven't found all of them yet, keep going, because we know that there might be a path. Or you can keep going to, you can keep going until there are no more intersections in the city, because on average it's going to be at the same time, right? In the same call, if you keep covering all of the intersections in the city and then backtracing only from the intersections of interest, it's going to be around the same time, right? Okay, so yeah, we don't stop until we reach one destination, we keep going. And in this case, for example, we will continue wavefront expansion and we see that, okay, we are able to find the optimal solution to this intersection as well, and, and this intersection as well, okay? Once we find all the intersections of interest, we backtrace from there and find the optimal solution or the travel time solution from milestone 3 function. And if you understand the Dijkstra algorithm well, you will notice that it's not a much of a code change to actually implement this. All you need to is, instead of saying that if I reach my destination then return, keep going and try to find all of the intersections that you are interested in. And then you can look them up out of an order map or something. It's up to you what kind of data structure to use. But it's like around 3-4 line of code of change of code. Okay, so let's look at the number of calls now. Okay, so you are using a single source to all the destinations in the city. And what do we need here? We need any delivery location to any other location. So that's around 2 n calls, right? Because we will call one of these algorithms multi-destination Dijkstra from every, where the source is every single intersection of interest, right? So that's around 200 if, let's say, n is 100, equal to 100. Plus, we need any depot to any delivery location. So that's around D calls, because we will call for the multi-destination Dijkstra from each single depot. Okay, so if let's say D is 10, that's around 10 calls, plus any delivery location to any depot. But actually we don't need that, right? Because we can get it earlier from these calls by keep expanding from the wavefronts until we reach all of the depots as well, as long as the other intersections. Yes, Dante.
So you mentioned that there's going to be like a few lines of changes. My only question though is that beyond the idea of expanding Dijkstra until we reach every intersection, couldn't a problem arise if, let's say, 2 different intersections you're reaching go through the same node, and then they split up after that, so the back edge has a different ID for both and overwrites one of them?
But what's the problem in that? So all of Dijkstra is doing is, what is it trying to do? We're not backtracing yet, right? What Dijkstra is doing is just expanding the wavefront and registering that whatever node I am at right now, this is the edge that I used to get to it, right?
Yeah.
So this is what we register only in Dijkstra and the best travel time to reach that node, right? So for every single node. When we backtrace, then we are visiting the other data structures to see what is the best current time, and then we backtrace from each edge to reach the source, right? So it doesn't matter if two paths split, right? Yeah.
It's the best travel time you're saying to that.
Yeah. And that's actually one of the good things about Dijkstra, is that as long as if two paths will intersect at one point, we know that the best travel time to get to that point is the same common path, because this is what Dijkstra does, right? It guarantees optimality. Yeah. So again, we have 2n calls from each delivery location and d calls, and then from any delivery to any depot, we can just rely by keep expanding from the first line here, right? So in total, we have 2n plus d calls, so that's around 210 calls. Okay, so is this the minimum? No, we can also optimize the any depot to any delivery location, and that's one call with multi-source to all destination. And so you can improve a bit better and make it multi-source instead of just one source, right? But that's only recommended in the depots case, because the number of depots are around 10 to 20 depots, so it's easier to manage multi-source Dijkstra. We're not gonna go over the details here, but yeah, you can also further minimize this number 10, d equal 10, but that will only save you like 10 calls, right? Okay. So it reduces to 201 path searches in total. Okay, so let's look at the complexity. So let's say we have k intersections of interest, where k in this case is going to be equal to 2 times n plus d, right? The number of delivery pickups and drop-offs plus the number of depots, okay? And let's say we have a graph of v nodes. So let's see if this is fast enough. So the total complexity here is what? We are looping over k intersections, and from each of these intersections, we are calling this multi-destination Dijkstra, right? So what is the time complexity here? Let's see. So Dijkstra algorithm can search the whole graph. Oops, I actually should have asked you this question, but yeah, now I'm showing it. So Dijkstra is going to show the whole graph, right? Search the whole graph, and usually it will with the multi-destination Dijkstra. So you can keep going until you finish all of the map. You don't have to stop at just the intersection of interest. And what do we know here? We know that there are O of V items to put in the wavefront. So in total, we're going to put, let's say, all of the intersections in the city inside the wavefront, in the worst case. And because we're using a heap or a priority queue to insert or remove nodes from the priority queue, that's O of log V. So in total, one call of Dijkstra search, multi-destination Dijkstra, is going to be O of V log V, right? And because we are calling this k times, which is the number of intersections that we're interested in, then it's going to be O of k V log V. Yes?
So can you just go back to the one slide before?
Yeah.
I don't understand what you're returning from the multi-destination Dijkstra.
You don't understand what we're returning?
Yeah.
Okay, so in each call of multi-destination Dijkstra, what we are trying to do here, we are trying to find the path from whatever source we are interested in. So one of these 2n plus d intersections, or one of these k intersections, this is going to be our source. And then we're going to keep expanding in multi-destination Dijkstra until we form a path, or until we find all of the other intersections of interest, right? All of the other k intersections. So, and then we're going to stop. Once we do that, we're going to backtrace from each of these k intersections back to the source, okay? And that will give us the path, and it will give us, you can compute the best travel time to go from one intersection to the other and store it in that big matrix, right? That we're going to use in milestone 4. So remember in the last lecture, we discussed that To do the greedy algorithm, we're just gonna estimate the travel time from one intersection to the other by the geometric distance, right? Yeah. And do you agree that it's not as accurate to rely solely on the geometric distance, right? Okay, so here we are trying to better estimate the travel time to go from one intersection to the other by actually calling the M3 function, right? But we found that if we just call the M3 function from every intersection to every single intersection, is going to be very slow. And that's why we rely on multi-destination Dijkstra.
So you call this multi-destination Dijkstra, once for every intersection?
Yes.
You build like each one is like a row in the matrix?
Yes, exactly. Each one is gonna build you a row in the matrix to go from one intersection to all other intersections. Yeah, makes sense. So, okay, so the time complexity for this is going to be k v log v. And let's turn this into actual time. So one Toronto search can execute in around 0.1 seconds. Like that's based on the A-star algorithm. But we agreed here we're not gonna use the A-star algorithm because for our use case, Dijkstra is more useful because we are visiting every single intersection in the city. So let's say, but let's say even that will take around 0.1 seconds, right? So for k equal to 100, like let's say the number of deliveries is 100, we are gonna get around 20 seconds, which is good enough, right? Okay, so that's actually not accurate. Yeah, even if it takes 0.2 seconds, that's gonna be around 40 seconds, which is still good, right? Now, there are ways to further optimize this. Even if you don't optimize this, you're still left with a bunch of time to do a lot of other heuristics within the 50 seconds. So in Milestone 4, the goal is to keep going until you reach the 50-second limit, as long as you can still do better and trying to find better quality paths, okay? So, but you will allocate some time from this to basically build that matrix, right? So that's around 20 seconds, or even let's say 40 seconds. Now, the good thing about this, if you notice, is that we are calling this from every single intersection out of these k intersections to build one row of that matrix. But if you notice that these calls are independent from each other, you can do them in parallel and try to further optimize the time to build that matrix, right? Because you're going to access different indices in the matrix to store the results. You're calling these multi-destination Dijkstra from different source intersections, so they are parallel in nature. Okay, and if you look at the UG machines, we have around 8 core machines. We have around 8 cores per machine, and that allows you to run like probably 16 threads in parallel, 2 threads per core. And why is that? Because computers these days, or like CPUs these days, cannot get much faster within one core. Why is that? There are a lot of physical constraints that I'm not going to go into, but there are physical constraints that prevent us from going faster. But because the size of these cores are decreasing, we're able to fit more cores per one chip around every 2 years, and that's called Moore's law if you haven't heard of it. And that because the transistor size is decreasing and the number of transistors that we can fit on the chip is more. Okay, so this allows us to place as many cores on the chip as possible. So in some of the machines that we use at Cerebras, for example, they contain 64 or 128 cores. Okay, so if you have a problem that is parallel in nature, it's a good idea. It's always a good idea to just throw parallelization on multi-threading into it and make it faster. Okay, so instead of this 20 seconds, you're probably going to save more time in it. Okay, so my tutorials this week will go over how to do this multi-threading. It's generally a useful technique in any programming, but it's also like it's a very good and suitable technique for us in this case because we are calling multi-destination Dijkstra from different intersections that are independent from each other. Okay, so you don't have to do this again in Milestone 4, but it's a good technique that might save you a lot of time and leave you with a bunch more time to actually explore other good quality paths in your algorithm. Any questions on this? Okay. So so far we've covered only one heuristic, and we improved a little bit on it in terms of our travel time estimation, right? Which is the greedy heuristic. Now, the problem with the greedy heuristics is that they commit to their, once you find a solution, they commit to it and they don't change their decision back, right? So that might limit you a little bit in terms of the quality of the path that you're gonna find, or for the traveling courier. Okay, but what do we know here? We know that we have still a lot more CPU time that we can spend. We are given 50 seconds, why not use all of them and try to find better quality? So the problem is, like with greedy algorithms, you probably won't get much if you keep running. So let's come up with better heuristics. Okay, so one way to get a better answer is through something called multi-start, right? What is multi-start? Is basically, in the greedy algorithm, we start from a certain depot, let's say, right? And then we continue from that depot until we finish all of the traveling courier path. Multi-start tells you that, what if we change something in a little bit in the initial solution that we have, so that, and run the greedy algorithm again, we might get a better solution. If we do, let's take that, right? This is a technique that's widely used in any heuristic, and if you have a bunch of time, a bunch of CPU time to spend, why not just do a multi-start? So we can try our greedy algorithm multiple times until you find a better solution. But the trick is how to make the answer different. There are several ways to do that. Any ideas on how to do it? Like, we want to change what we choose initially, such that any decisions that come after that will change based on how the algorithm is running. Yes, go ahead.
I was thinking either, like you mentioned, you change your starting point, or we also like look several steps ahead to like change where you go next instead of just looking one step ahead.
You can do that, yeah. So, but that's not called a multi-start anymore. Like that's another heuristic that's actually useful as well. But your first solution is right. Like, can we start from a different point? Yes.
You could try like different heuristic functions, or you could like weight them differently.
Yeah, you can weight them differently. That's actually a good idea. But that's assuming that you have multiple heuristics you're running, right? Let's assume now we are only stuck with the greedy algorithm. But what do we need to change from the initial decision such that the whole path will change? But your solution is correct. If you have multiple heuristics, you can run some experiments and try to weight them differently, see which one is more important at which point in time, and it actually might get you a lot. Actually, some of the teams that won the competitions previous years, they use reinforcement learning on multiple heuristics, so that in each stage in each iteration, the reinforcement learning agent is basically choosing what is the best heuristic to choose right now, to run on right now. And based on how the algorithm is performing, I might change the weights on the priority of these heuristics in future iterations. Yeah, any other idea on how to tweak this algorithm a little bit to change the initial decision? Okay, so yeah, as Donnie said, one of the ways is to force it to start at a different depot. We are always, like, remember in the greedy algorithm, we are always choosing the closest depot, the depot that gets us closest to one of the k intersections of interest, right? But why not start with the second smallest travel time instead of the smallest travel time, and try from there? Maybe we're gonna get a better solution, right? Sometimes you can also do something like the weights, like have a 10% chance of taking the second smallest travel time whenever you're choosing each next delivery, right? So whenever I'm at a current delivery, in the greedy algorithm, what do? We just choose the next intersection that has the smallest travel time from the current intersection, right? But we're gonna tweak it a little bit, saying that we're gonna generate a random number from 1 to 10, and if the number is 10, I'm gonna choose the second smallest instead of the smallest. Maybe hoping at the end of the algorithm, we're gonna get a better quality path. But while you're doing this, you're always going to save the best solution that you've found so far, such that at the end of the algorithm, you're returning the best out of all of these multi-start runs that you did. Okay? There are other ways as well. Another good thing is that if you do a multi-start as well, you can also run these in parallel. You can run multiple greedy algorithms in parallel. Each one is starting at a different intersection, and hopefully you're gonna, at the end you take the one with the best solution, or the best quality of results. Okay, so let's look at our solution again, right? And see how can actually this benefit us. So let's say we start at this depot going to intersection A, and then we dropped off A, we picked up B, dropped off B, and then we ended at this depot, right? So that's one solution. Now, is this optimal? Probably not, because we are going back and forth across the city, right? So what if we use multi-start? Force route to start on the second best depot instead of the best depot. So in our greedy algorithm, this is the best depot to start at, because this is the closest one to an intersection. But in this case, we're gonna say that, I'm gonna start from here. I don't wanna start from that depot, right? So if we start from this depot, we're gonna go to B1, pick up B1, and then continue our greedy algorithm as is. The closest one is to pick up A1. We pick up A1, drop off A1, drop off B1, and then we're gonna end at this. It's better, if we can see, clearly it's a better final answer than the previous one, and that's just because we started at a different depot, right? So multi-start is a very good heuristic if you have a bunch of CPU time to spend. Just keep it running, change the decision at the beginning, and let's see if we get a better answer or not. Questions on this? Yes?
Wait, so you, does that mean you calculate like 3 different paths?
Yeah, so greedy algorithm does not guarantee the optimal path, right? So it's based on whatever decision you make now, your future solution is going to change, right? So if we change the decision that we make at the beginning, the whole path is probably going to change, because it's going to take different decisions later on. And that's clear from this example. Like, we just changed the depot that we're gonna start at. It ended up with a totally different solution that's actually better.
Okay, but how do you know if it's always going to be the right one?
We don't know. So that's the thing. So with multi-start, you're just hoping that you're gonna get a better solution. And while you're running with these different experiments, you're always going to save the best solution that you found so far, so that if you later on don't find any other better solution, you're just gonna go back to that solution and return it.
Oh, I see, that's what I was asking.
Yeah. Yes?
So if the initial best path is like 20 seconds, and we have a total of 50, isn't this second stage of finding the best path really quick? Because all you're doing is you're pulling those values from the matrix, like the matrices, and seeing from this current node which is the best time to the next node?
Yes. So the good thing about the greedy algorithm is that pretty fast, right? You're just like querying what is the travel time, but you have to repeat the whole algorithm. You're not just pulling from the matrix and just replacing the numbers, right? So you're gonna like kind of start the whole algorithm from scratch, as if saying that, okay, I have a path that starts at depot X, okay? But now I'm gonna start at depot Y. Let's see how the greedy algorithm performs. So you're not just replacing the travel time from here to here.
No, I meant like yeah, let's say you change the depot. Isn't it still pretty quick? Like
Yeah.
maybe a second or two, just for it to pull from the matrix what the best next intersection to go to is, and repeat that however many nodes you have?
Yes.
So like, can't you like try this like many times?
Yeah.
30 seconds?
Yeah, you have a lot of time left. You can do as many things as you want within this time. And if you have like 30 different ways to start from, why not just try these and let it run and see if you can get a better solution.
Yeah.
So that's one way, right? Like the greedy algorithm, it's very fast, so it allows you to do that. But we're gonna see next that a lot of other heuristics that might not be as fast, but they are actually, they can be better. You can still use the multi-stop, but it's not gonna be as many, right? Okay, so yeah, that takes us to our next heuristic. It's called iterative improvements. So again, the problem with the greedy algorithms is that they commit to the decision that they take. So once they make a decision, you're not gonna go back, they're gonna take that and continue to the end of the algorithm. Now, with iterative improvements, we start, let's say, with a greedy solution. Okay, like it's a full path. And we look at that path and say that, okay, I'm gonna tweak, let's say I'm gonna just tweak 2 of these intersections, maybe swap them or somehow, and see if I get a better solution. And I'm gonna continue doing this as long as I have more time to spend. So this is called iterative improvement. We're starting with a certain solution and just keep iterating on it until hoping we find a better solution. Okay, so what do we mean by that? So we're just trying to improve the existing solution. We found a solution that works well, like it's a good quality, but now we are trying to improve our quality, right? So let's say we have this example again. So we're starting at a depot, picking up D, dropping off D, picking up whatever. We have all of this path, okay? From now on, I'll stop showing the city map just to minimize clutter, and I'm just gonna show you the path with the intersections of interest, okay? So this is our path, and these are our intersections that we're trying to find. On top of these, I'm basically listing on the edges the best travel time from the multi-destination dark that we found to go from one intersection to the other, okay? So if we look at this solution, this is taking total travel time of this is 81 seconds, okay? Now we are trying to do something better. With iterative improvements, we can come up with a lot of different techniques that allows us to tweak the solution somehow, and hoping we're gonna find a better solution. Okay, so we call these local perturbations. We're just gonna choose like 1 or 2 intersections and perturb them in a way that will generate a totally different solution, okay? Okay, so any ideas how to, like what kind of perturbations we can do? There's no like right or wrong solutions here. We're just trying to change the solution somehow. We're given a path, you're looking at it, and we're just gonna change it somehow. Okay, so one way is to randomly swap the order of two intersections, right? So if you, for example, swap the order in this path between B and C, what we are gonna get, like, so initially we're going from the pickup C to drop off B, and then drop off C, right? But let's say that we're gonna swap the order of dropping off B and C. So we're gonna drop off C first, and then drop off B first. Did we get a better solution? Let's see. First of all, because of the legality constraint in milestone 4, we have to check if the new solution is legal. Because you might swap the order of 2 random intersections, and you end up dropping off one package before picking it up, right? So the first thing that you need to do is to just make sure that it's still legal. In this case, it's still legal. We just, we have C, and we are dropping it off just before B, and we already have B. Okay, so let's compute the new travel times from the matrix that we built. So in this case, we know that this is going to take 23 seconds and this is going to take 14 seconds. But the overall travel time right now is 72 seconds. So it's much better than the 81. So in terms of quality, we found a better solution by just swapping the order of 2 intersections. Now this is not guaranteed. We're not guaranteed that we're always gonna find a better solution. But we do this as many times as we can in the hope of one of these solutions will get us a better solution. We save that better solution somehow and continue improving. If we don't find any better solution, we'll just go back to the best solution that we found and return that solution. Okay? Any questions on this? No. Okay. So swapping is one way to perturb the local solution, to locally perturb the solution. There are more powerful solutions as well. You can always go read the literature to find perturbation solutions for any kind of MP hard problems, computational hard problems. And the traveling salesman problems has a lot of literature on it that will show you like a lot of different techniques people try. Okay. So the problem with the swapping 2 intersections, it is a limited change. It's not gonna give you much information, right? So maybe a bigger improvement, maybe we can try bigger improvements that are possible with radical perturbations, like significantly different from the initial solution that we started at. And one of these ways is called a 2-edge perturbation, or called a 2-opt. It's a very popular technique in traveling salesmen. It's widely used. It works really well with traveling salesmen. It works well with the milestone 4. It's just not to the same extent as traveling salesmen just because of the legality constraint. We're gonna understand why in a little bit. So what 2-opt or 2-edge operation tells you to do is that you're going to delete 2 connections from the path that you started at. That will cut your path into 3 different pieces, and then you'll choose a different order to connect these 3 pieces, right? So let's say, in this case, I'm going to cut this long path, and I'm gonna also remove this edge, right? So now we are left with 3 different pieces, this piece, and this piece. And we want to connect them somehow, okay? So we decide to connect them this way, okay? So we're gonna reconnect the path differently. Now, when you reconnect, you will notice that you're probably gonna end up with either a legal solution or not a solution, because in this case, you are visiting the depot while still you're visiting this node from 2 different intersections, and the order is not clear anymore. So the first thing that you need to do after a 2-opt operation is to fix up what we call legalize the solution, okay? So we may need to fix up the depots to make the solution legal, and in this case, I'm just going to remove this edge and connect it this way, reverse this edge, and then remove this depot and end up at this depot, okay? Does that make sense? Might be too much. So let's go back. Okay, we started at this solution. We deleted these 2 edges, the 23 seconds one and the 5 seconds one, okay? We are left with 3 different pieces, and we decided to connect them this way. Again, we don't know if this is a good solution or not. We're just hoping to find a better solution. Now, when we connected them this way, we ended up with not a legal solution even, because if you notice here, we are visiting this node from this node and from this node. So one way to fix up this is to just reverse this edge. So this gray edge will be reversed, and it will go from here to here. The other thing that needs fix up is we are visiting the end depot in the middle of the route, right? And it's unnecessary to do that. We need to end up at the depot, so just remove the depot edge and try to connect it differently from another location. And in this case, we're gonna connect it from the last intersection. Now, to make this easier, you can actually disconnect all of the depots from your initial solution and just focus on changing the order of the delivery intersections somehow, okay? So that this will make the solutions less illegal, and fixing them up is going to be easier. At the end, you can always take the best depot to the source and best depot to the destination. Okay, so let's calculate the total travel time of this. Now, remember, the prior one was 71 seconds. In this case, we are able to find a better solution that takes 70 seconds, which is a better quality one. So that's another technique for iterative improvements that allows us to repeatedly trying to change all of these solutions until we find a better one. Yes?
So can you re-explain that last part on disconnecting the depots?
Yeah, so notice here, when we started with the initial solution here, we have the depots connected, right? We starting at this depot and end at this depot, right?
The red and blue line.
Yes. And when we did our 2-opt operation, we ended up with an illegal solution that we had to move the depots somewhere.
Yeah.
So one easier approach I'm suggesting is that from your initial solution, ignore the depots, ignore where you're starting at, and only focus on the path that starts at this node here and ends at this node here, okay? If you ignore these and just apply the 2-opt operation on this, fixing the solution is going to be easier now. All you need to do is like reversing some edges or removing them, right? You don't have to move the depots around.
Like if you just connect the new starting point with the closest depot and the new ending point with the closest.
Yes, at the end of the, once you get a good solution that you are comfortable with, I'm just going to connect the closest depot to the source intersection and the closest depot to the destination intersection, or the last intersection in my path, okay? Because that's gonna give me a better quality, right? Like we know that this is the best we can do. Okay. So anything else we can do here? Like in the classical traveling salesman, which is which doesn't have this legality constraints, there isn't much you can do, right? Like you're just gonna apply to-opt over and over again, hoping that you're gonna find a better solution. If you do, you update the solution and apply the to-opt again on top of it. So in our traveling courier, there is the constraint that, first of all, whenever we make any move, we have to check if the path is still legal, if it's still a delivery order. Remember, we have to pick up a package before dropping it off. And we have to make sure that there are no reverse edges that don't make any sense, right? And again, to-opt works very well with traveling segments. There is a lot of literature on it. You can actually inspire from those literature for this milestone as well, if you go read some papers on it. Okay. With traveling courier, you might get less gain from the to-opt just because of the legality constraints. So a lot of times you'll probably just reject the new solution just because it's illegal and it's very hard to fix. You're just gonna ignore it and try again. Okay. So, okay, let's look at this in a different way. So trying to escape local minimum. What are local minima? So let's look at this example here. So we're starting at this depot, and we're visiting in this order, 0, 1, 2, 3, 4, until intersection 9. Okay, so, whoops. Let's try one of the local perturbations techniques that we'd learned to try and find a better solution. So can we swap the order of 2 deliveries? Any ideas? Are there any 2 intersections we can swap here to find a better solution? Yeah.
Maybe like, you see how like after Moses cluster said that you have this cluster and said you travel to the next path, maybe it would be better if you travel from one place to another place. But I just woke up, so I don't really know what
can you repeat the last part?
I don't know what those to swap.
Oh, okay, you don't know what those to swap. That's actually fine, because in this case, whatever you swap, you're probably gonna end up with a worse solution. So let's say, for example, that I'm going to swap these edges, okay? So instead of going from 1 to 2, 2 to 3, I'm saying that I'm gonna go to 1 to 3, 3 to 2, 4. That's obviously a worse solution, right? Like, we're going back and forth across the city now more than before. So, we are out of luck. Even if you, for example, change from 3 to 4, like go 3, 7, and then whatever, 7, 6, and 4, 8, whatever, again, you'll end up with a worse solution. So in this case, we say that we are stuck in a local minima. A local minima is basically where, given we are at a solution, and if we keep swapping more and more, we're not gonna be able to get out of, because we are kind of at the best solution that it might not be the most optimal solution, we don't know if it is, but we are stuck in this case, in this point, that we're not gonna be able to go out of, and on whatever number of iterative improvements we're trying to do, we're stuck there, okay? You had a question?
No, I was gonna say, like, what if you were to, like, maybe to go back to the previous image?
Yeah.
What if we were to get rid of 2 to 3 and 6 to 7, and then you connect 2 and 7, and 9 and 6, and you just change the depots?
2, 7,
and
9, 6,
and you just
and then change.
to the depot.
Yeah, okay. You might end up. So you're basically. But what are you swapping here? We're not doing swap anymore, right?
2 to 3 and the 7 to 6.
Yeah. In this case, you're cutting them. You're using kind of the to-opt. You're not swapping the 2 edges. Yeah. Like we're talking about the swap here. Like we're stuck at the local minimum with the swap. But yeah, like with the to-opt, you might find a better solution. No.
So how is that an intersection swap, the zigzag?
This. So we are swapping 1 to 2 and 2 and 3. Okay. So what we are saying is that, like, we are swapping the order of 2 intersections. A swap is you take 2 random intersections and try to swap their order. So instead of going 1, 2, 3, we're gonna go 1, 3, 2. Does that make sense?
Kind of. There's multiple options for how you can swap it.
Yeah. There are like you can count them. It's like n squared options to swap from. You can, yeah, in your iterative improvement, you can try them all actually. It's very fast to just swap to intersection and try to calculate the new travel time, right? Yeah. Okay, so yeah, let's look at the 2-opt case. So we try, as you suggested, Dante, we're gonna remove 2 and 3, 2, 3, and 6, 7. And now the path is cut into 3 pieces. One option is to connect them this way. Instead of 2, 3, and 6, 7, we're gonna connect them 2, 6, and 3, 7, and then try to fix up the solution by reversing the second path. So we reconnected this, it's probably worse, or like kind of the same quality. Another solution is what you suggested, is to go 2, 7, and 9, 6, and fix up the path here by reversing it and changing the depot, right? So reconnected differently, now it's a better solution, right? So we found a better solution. We were able to get out of our local minima by just changing the heuristic technique that we used, right? What I'm saying is that, like, if you stick with one heuristic technique or one operator to do the iterative improvements upon, you might end up with local minima that you're not going to be able to go out of unless you change the whole technique that you're using. Okay. So with a more powerful permutation operator, you can escape local minima further. Okay. Now let's look at the ability to escape local minima versus the number of choices that we can have out of each operation and the probability of being illegal. Okay. So let's look at the 2-opt complexity. In swapping order, you can just choose any 2 intersections, and you can how many options you have? You have n choose 2 options to choose any 2 intersection. Okay, in this case, let's look at the number of options we have if we are doing the 2-opt solution. So what are we given here? In any path of our traveling courier, we're going to have at most 2 n-1 edges, connections, which are connections between delivery locations. So how many different 2-opts we can have out of this? If we calculate this, first of all, we need to choose 2 edges out of these 2 n-1 edges to basically cut our path from. So this is a choose operator, so 2 n-1 choose 2, that's around 20,000 options, okay? If we have n equal to 100. And then for the 3 subpaths, we have 6 ways to connect them, right? 3 factorial. So that's 6 ways. And for each of these 6 ways, we have to go over each of the paths and decide whether we need to reverse it or not. So that's around 2 to the 3 options. So that's around 8 options for each of the 3 paths. Okay? For each of the 6 ways. So yeah, okay. So for each 2-opt operation, we have 8 times 6, 48 ways to decide whether we're gonna reverse or recombine the paths. Okay, so in total, if you multiply that by 20,000, we're gonna get around 1 million 2-opt options that we can try to find a better solution from each single existing solution that we have. Okay, if your code is fast enough, you can try them all of these 1 million. You're left with like whatever, 10 to 30 seconds. And if you find a better solution, you can commit to it and then try the 2-opt again and again. So that's good enough. Now the problem with 2-opt again is that a lot of these options might be illegal and will be thrown away or like trying to wasting time fixing them up. So that's why people try to find other perturbation techniques that might work better for our problem. Okay, so as I said, many of the 2-opts will be illegal. We prefer, like, maybe one way to fix this is I'm going to prefer the small ones. Like, I'm going to cut my path into the small pieces, or like one of the pieces will be very small, and I'm gonna focus only on fixing up that piece. If the other pieces are illegal, I'm just gonna throw away my solution and try something else. Okay? So basically legalizing the path or trying to fixing it up will be much faster if I'm just gonna focus on the small piece. Okay? You can come up with your custom or novel perturbation as well. So one way to actually do this is to use what we call a 3-opt instead of a 2-opt. Now the 3-opt is going to cut the path into 4 different pieces instead of 3. So it's more powerful because you have more options to how to reconnect your path. The problem is you're probably going to end up with also more illegal solutions because now it's going to be much harder to fix them up. So